Yes, recording. Thank you,
Yes.
Melissa. Uh, all right. Hi, everybody. Let me get to the right thing here. Okay. And start my slideshow. Okay. All right. Uh, great. So, hi, everybody. My name is Sarah Greenstreet, and for now, we are going to be covering session number 10 for the Data Academy on solar system catalogs. Let's see, can I advance my slides? There we go. Okay. So if you are uh, new to the Data Academy, if this is the first time that you are attending this week, Melissa did just talk about the schedule, but this year we're really focused on helping people be able to learn how to use the Rubin Science platform at a beginner level and how to access the Data Preview 1 data products. And so all of our sessions are repeated more than one time throughout the week. This solar system catalog session is going to happen both in the first and second chunks of sessions tomorrow. Again, as well, it's all the same content, so you only need to attend any one of the sessions on a given topic once to get all of the information covered. And I am not checking the chat, but if someone can share the link to the slides for me, that would be great. They are available on the Rubin Data Academy GitHub page as well, so you can access them there. And we'll put all the recordings from the sessions as well up there later. So if you miss one, there will be recordings available later. Okay, as a reminder, the best place to get help from Rubin staff is to use the community forum, which you can get to at community.lsst.org. If you go to the support category, which is shown on the bottom of the screenshot on the right, from there you can make a new topic and you can give your topic a descriptive title so that we know what it is that you need help with. If you have a question or any issues with the data products or the services or tools or anything like that, give us a good description of some of the specifics about what it is that you're having an issue with. If you can copy and paste error messages or give us screenshots or things like that, that really helps us out. So we can try to get you help and a solution as soon as we can. So the Data Academy is all focused on Data Preview 1. So everything that's covered in all of the sessions are about DP1, except this one is slightly different. We're going to cover both DP1, and at the end, we're going to talk a little bit about Rubin First Look, since there's some solar system stuff that's relevant to that as well. So the first part is all going to be about Data Preview 1 itself. All of the documentation for DP1 is at dp1.lsst.io. There's also a paper in the works for DP1. There's a draft version called RTN 95, and there's a link in the slides here that you can get to with that as well. And if you're starting to write papers with DP1, which is great, there is a DOI in the documentation for that DP1 paper as well. Okay, so for this session, our agenda today, we're going to cover quite a lot of stuff. We're going to try to briefly go through some of the data processing for solar system, a little bit about difference image analysis, and then go through solar system processing and linking of moving objects. We're going to talk about the data products that are solely related to solar system objects, and then also the one that is related to solar system objects as well. So we'll go through those four tables. And then there's a whole bunch of tutorials listed here. We're not going to have time to go through all of them, but we'll do a tutorial a bit on how to use the portal, and then we'll walk through one or two of these notebooks as well. But I listed on this slide here all of the notebook tutorials that are relevant to solar system science and the data products, and starting to analyze some of those data products so that you've at least got a list here of what's relevant. And then at the end, we'll do a little bit of looking at some of the solar system object discoveries from Rubin First Look as well. Okay, so some of the key concepts that are important as we're starting to talk about all these data products and things that are in DP1 are image subtraction, which is when you take a template and you subtract it from a visit image to create a difference image. So all of the non-static sources remain in the difference image. Then difference image analysis is performed on that difference image, trying to pull out all of the sources in that difference image. There are two types of sources relevant for solar system. One is a DIA source, or a difference image analysis source, and an SS source for a solar system source. So there are specific definitions that LSST uses for these terms. A DIA source is a detection in a single difference image, so any non-static source. And then SS source is something with a signal to noise ratio greater than 5, moving object detection within that single difference image as well. So specifically, a moving object detection is the SS source. Tracklets are another key concept. Tracklets are defined as two or more detections, so DIA sources or SS sources, of a single moving object that are taken in close succession in a single night. Um, and I should say as well, for the DIA sources and the SS sources, they are very similar to each other, but there is a table for each one of them within the data products, and they have slightly different information in each of them about that detection from the difference images. SS objects, these are another thing that have a specific definition for LSST. So an SS object is a moving object for which groupings of DIA sources or SS sources have been linked together. So keeping these key concepts in mind, I just want to briefly walk you through the processing for solar system and how the daily data products for solar system are made. So this infographic you can find at down here in the bottom right at dp1.lsst.io, where all of the documentation for DP1 lives. You can find this infographic there as well with a more in-depth description of each of these different steps. So just quickly, I want to walk everyone through this. So we start during nightly observing. While the telescope is observing, alerts are going to be produced within 60 seconds for all of the signal to noise ratio greater than or equal to 5 DIA sources. And those DIA sources that are associated with known objects, known moving objects, are going to include the matching SS object catalog in the alert that goes out. So throughout observing at night, alerts will be produced every night. After observing is over, most of the solar system processing pipeline runs during the daytime. So all of that newly collected data from the previous night's observing is then passed to the moving object linking algorithm. So that's step 2 here, where we discover and link new objects. Now that's a whole process and pipeline in and of itself. So there's another infographic here as well for how specifically the tracklet linking and the orbit fitting happens with this software algorithm called HelioLink 3D. So after the nightly observing happens, the nightly DIA source catalog is ingested. All of the individual sources that are unattributed to something else are pulled out of those nightly DIA sources. And then the make tracklets function will connect and make tracklets for the candidates from all of those unattributed sources. Those candidate tracklets will then get passed to HelioLink, and they will be linked together. So candidate tracklets, where you have a minimum of 3 of them over 3 to 14 nights, will then get linked together using this specific step within HelioLink. Once the linkages are made, then they're passed to a function called link purify that will refine those tracklet linkages, doing things like orbit fitting, and outlier rejection and deduplication and things like that. Then the refined linkages are run through a process of associating them to any known objects, as well as searching for any precovery observations that Rubin may have made of those specific objects. And then all of those associations and all of the discoveries are submitted to the Minor Planet Center. So this is a very, very quick overview of how this process works. Again, there's more information in the documentation if you go to dp1.lsst.io. So that's all just for step 2 here of how we actually discover and link new objects. Those discoveries and associations to known objects are passed to the Minor Planet Center. The Minor Planet Center then does all of its processing of everything that was submitted. It then produces its MPC orb catalog of all of the orbital information for those objects. That new daily MPC orb catalog is ingested back into the solar system processing pipeline, and then all of the relevant information is also updated in the SS object, SS source, and DIA source catalogs as well. So that we then have those 3 updated catalogs as well as the updated MPC orb catalog that then are all released as new updated daily data products. So this whole process runs every 24 hours and will continue through the entire process for LSST. And so for DP1, this whole process was essentially used in a slightly less automated way so far. There are some small differences between what's going to happen in the regular processing and specifically what was done for DP1. And again, all of this information is on the documentation page. The 2 key parts were associating sources with known solar system objects and discovering these previously unknown objects by linking these sets of tracklets. So I'm not going to go through all of the specifics here, but it's very similar to the process I just mentioned. One thing that I'll note is the last bullet point here, and I'm just going to read it out loud. So the inputs to the HelioLinks suite for the discoveries in particular include all of the sources detected in difference images produced by an early processing of the LSST ComCam commissioning data, including some of the images that were later rejected as part of DP1 processing and hence are not part of this DP1 release. So in order to get the discoveries, there were additional images that were used that are not actually part of the full data release that came out for DP1. So that's a caveat to how these discoveries were made and the processing for DP1. Okay, so before I ask for questions, let's talk a little bit about these different data products and these 4 different tables that are relevant to solar system objects. So the first is the DIA source table. This one is accessible both via the TAP service and the Butler, and there's examples here of how you can access the DIA source table, both for the Butler and for in the TAP service. There's a specific name in the Butler for each of the tables. Same thing for the TAP service. In the TAP service, they're all DP1 dot and then the name of the table. Here are the columns and the number of rows as well in the table and some of the key columns. So the DIA source table mostly has information about the visit and the band and the RAN deck that the source was at and the flux information. There's also the SS source table. It's also accessible via both the TAP service and the Butler. And again, the names are on here for how to access this table in both the Butler and the TAP service. SS source, has a lot of information about the heliocentric and topocentric position and velocity vectors, as well as the phase angle for the SS source that came from the difference image detection. The SS object table are the unique SS objects that are groupings of detections that are linked together. The SS object table for DP1 has 3 columns and 431 rows, which means there are 431 objects in the SS object table. And lastly, we have the MPC orb table, which has the orbital parameter information pulled from the Minor Planet Center. This table is only available via the TAP service. It's not available via the Butler since it's not something that's actually produced by LSST. It's ingested from the Minor Planet Center. As you can see, this has nearly 1.5 million rows in it. So the DP1 MPC orb table includes a snapshot of all of the known solar system objects in the MPC database as of the 24th of March, as well as the known object associations that were made within DP1 and the discoveries for DP1 that were submitted to the Minor Planet Center by Rubin as well. Okay, so before I go on to the tutorials, I've seen some things popping up in the chat. Does anybody have any questions that haven't been answered in the chat or anything that anybody wants to actually ask? You can unmute yourself if you do. Okay, I will continue then. Okay, I know there's been a lot of information with all of the processing. It's a lot to try to um, digest. So, okay. But we have tried to have good documentation on all of that as well. So hopefully that will help answer any additional questions that you have. Okay, so let's go to some of our tutorials. So let's see, I am going to exit out of full screen here. Okay, so let's go ahead and go to the Rubin Science platform, and we're going to walk through using the portal. So if you go to data.lsst.cloud, hopefully you've been able to sign up for an account for the Rubin Science platform and that it's been approved. If you're able to log in, then please do, and you can follow along with this. So this is the landing page for the Rubin Science platform. There's three different aspects. First, let's go ahead and explore the portal aspect. So if you click on the portal, this is the landing page. So up at the top, you can see a number of different catalogs here. If you were familiar with DP 0.3, these were the catalogs of simulated solar system data products for LSST prior to DP1. So you can access all of those here if you so desire. But for now, we want to look at the DP1 catalogs. So for DP1, everything is all lumped together. So in DP 0.2 and 0.3, the solar system stuff was pulled out as a separate thing, but now they're all together. So you can see at the top the different table collections. As a default, we get the DP1 tables. And then if you click on the right here, you can see the list of all of the tables that are available for DP1. At the bottom are these three solar system specific tables, and the DIA source table is in here as well. So just as an example of looking at one of these tables, let's go ahead and look at the SS object table. This one only has 3 columns, so it's not very complicated. But when you look at this, you can see each of the different columns that are in here. You can select any one of them if you want. You could select all of them if you want to. Um, uh, and as you're looking at this, it's kind of an easy way, the portal in general is an easy way to start getting used to what either the schema is for these different tables or kind of just what's in the tables themselves. So if we select all of these columns, since there's not very many of them, we can just go ahead and hit the search button and we'll just return all of the SS objects and all of the information that's in this SS object table. So automatically we get a plot here that is just taking the first 2 columns returned from the table and plotting the points for us here. So we've got the discovery submission date, which is the date that any discoveries that were made by Rubin were submitted to the Minor Planet Center, and the number of observations here. As you can see on the right, these are the contents of the table. It looks like the discovery submission date for most of these objects is just blank. That's because they're not actually the discoveries. If we click on the name of this column, it will sort this column for us. This is in ascending order. If we click it again, it's now in descending order, and you can see that there are now entries here that have non-zero discovery submission dates. So these are the objects. So we're looking at 100 out of 431 objects. You can see down here, there are in fact 93 solar system objects here that are discoveries that have a discovery submission date for the Minor Planet Center. If you select different objects in the table here, you can see that they will highlight themselves over here on the left as well. You can also, as you're looking at this, be able to get just the discoveries if you want by being able to put some limit value on the column here. So if we put greater than 0 in the discovery submission date column, then we'll only get returned the 93 objects that are new discoveries from Rubin in here as well. So this is a really simple table and a simple example of this. But if we go back to the slides here, there's a slightly more complicated query here as well. So in addition to being able to, sorry, I'm going to go back and forth here a little bit. If we go back to the DP1 catalogs tab, in addition to having the UI assisted version of being able to access the table information in the portal, you can also click on Edit ADQL up in the top right corner, and you can put in your own ADQL query here if you want to do something a bit more complicated without having to input all of the parameters manually within the columns. So if you go to the slides, if you have a copy of them, you can just copy this query here in the slides. So I'm going to copy this and then go back over here to the portal. And I'm just going to paste this into the ADQL query box here. And then I'm going to hit, well, let me tell you what this is first, actually. So this specific query, we're going to retrieve the pericenter distance, eccentricity, inclination, the SS object ID, which is the unique identifier in these tables for all of the SS objects, and the MPC designation, all from the dp1.mpcorb table. We're also going to grab the discovery submission date from the SS object table as well. So we're going to join the MPC orb table and the SS object table together on this unique identifier that's the SS object ID that is in each of these tables that's unique to each object. Okay, so then we're going to hit search. And we are going to get a plot again of the first two columns here. So this is the pericenter distance versus the eccentricity. You can go in here and change in the chart. Sorry, let me do that more slowly. You can go to the little gear icon here in the top right-hand corner of the plot, and this can change your chart options. So if instead of pericenter, you want to do the sum of major axis, which is not one of the columns in the table, we can change this to pericenter divided by 1 minus the eccentricity. And we can change our x-axis label here to sum of major axis so that we know we've changed this to something else. We click apply, and then we can close this window here. And now you see that we've got sum of major axis versus eccentricity. And this is for all 431 solar system objects in the table here. Again, if you want to just look at the discoveries as a quick way to know, like here, there's one Jupiter Trojan. Is this actually a discovery or not? Again, you can go to the discovery submission date column, and we can do greater than 0 here in the parameter box and hit enter. And this will refresh with just the discoveries that were submitted by Rubin to the Minor Planet Center. You can see here now that our x-axis range, or semi-major axis range, has uh, shifted as well. So that Trojan is not actually a new discovery. It's one of the objects that were associated with a known object already. So this is an example of how you can use the portal just to kind of get an initial feel for what the data is like and what is in these different tables. Okay, so let's go ahead and just go back to the home screen for the Rubin Science platform. And I'm going to go back to my slides for just a minute. Uh, and so next, let's go ahead and look at one of the tutorial notebooks. So as I mentioned at the start here, there's a number of different notebook tutorials that are related to either the solar system data tables or trying to explore some of the target fields for DP1. So for each of the data tables, there is a notebook tutorial that will walk you through the basics of what's in the table, how to access all of the columns, how to access the table both via the tap service and from the butler. It just gives you a general sense from the notebook aspect of what's in these columns or in these tables. In addition, there's also one of the target field exploration notebooks in the 301 series of notebooks that specifically looks at the low ecliptic latitude field. And so in this one, you can look at what the images are, a bunch of information about this specific field and the visits that were in that field. And then at the very end, there's also an example of how to retrieve all of the solar system objects that were detected in that field. We also have a series of notebooks, the 308 series that are on solar system science specifically. There's two of these notebooks so far. There's one that just helps you be able to pull out all of the discoveries out of the solar system objects. And then there's one that goes a little bit farther and looks at the orbits specifically. So we're going to look at this notebook, 308.2 on orbits. And then later we're going to, as I said, we will get to the Rubin first look things as well. So let's go back to the Rubin Science platform. And this time we're going to click on the notebook aspect. This is the startup screen for choosing your server. For the notebook aspect. Generally, you want to choose the recommended weekly image here, and by default, it's going to give you a large server as well. So we're just going to keep these options the same and hit start and wait while it spins up our server, which hopefully won't be too long for anyone. And I'm going to take a drink of water while it's spinning up. Okay, there it goes. Okay, hopefully it doesn't take too long for anyone. Okay, so when you go to the notebook aspect of the portal, there's this welcome page that you first land on that just has some information about this part of the RSP and links to the documentation and that kind of stuff. To get to the tutorials, there's this very handy drop-down menu from the top up here called Tutorials. And you can see that there's tutorials here from the old DP 0.2 and DP 0.3. And now there are new tutorials for DP1. We have a couple different series of notebooks here. The 100 level are all focused on different aspects of how to use different aspects of the Rubin Science platform. And each of these have a number of different tutorials. So if you're curious how to do something, it's a really good reference point for trying to figure out how to do something that you're trying to do. We also have a bunch of the data products tutorials that are the 200 level, and they're split up by different categories. So those catalog tutorials I mentioned are in here as well for the solar system specific tables. and the other solar system related table in here as well. And then we have our science demos. And I'm going to go down here to the 308 series for solar system. And we're going to choose 3082 to look at the orbits. If you have opened one of these notebooks already previously, you will get this little pop-up screen that asks if you want to overwrite the file that you had already opened before. If you haven't opened it before, you won't actually see this message. So I'm going to go ahead and click on overwrite so that I get a fresh version of this notebook. Okay, so at the top of the notebook, we always have these headers that just give you some information about the release that the tutorial uses and the last time that it was verified to run, so that you know that we're keeping everything up to date, the size container that this really needs, and which data release this is for. So here, this tutorial is really just looking at an overview of the solar system objects in Data Preview 1, specifically looking at their orbits. So we're going to use both the MPC orb and the SS object tables, and we're going to use the RSP package. So to start, we're going to import all of the packages that we need, and then define some of the parameters. So we need to be able to create an instance of the TAP service to start so that we can actually access these tables via the TAP service. And then we always try to make sure that we are using colorblind friendly colors when we're making all of our plots and matplotlib. So this cell is just making sure that we've got those color choices chosen here. And then next I have a function that will calculate the orbital classification for each of the solar system objects based on their perihelion distances and their eccentricities. So these definitions for all of these different classes, where the key to these abbreviations here are above this cell. These pretty closely follow what the Minor Planet Center uses, although they're slightly different. You're welcome to change these values if you wish as well. But these are the definitions that we're going to use for everything from the different classes of near-Earth objects to different types of main belt asteroids and Mars-crossing asteroids, out to the Jupiter Trojans and Centaurs and TNOs. And we'll even define the parabolic and hyperbolic asteroids in here just for fun. So we'll go ahead and execute this cell to get our function defined. And then we are ready to actually do our query. So this tap service query looks very similar to the one we used in the portal here. So we're going to pull out some of the orbital information from the MPC orb catalog, and we're going to get the discovery submission date here as well from the SS object catalog. So we're going to join these two tables together on the SS object ID. So we'll set up this query, and then we're going to run the query, which should just take a few seconds. We now know that it's completed, and we're going to go ahead and fetch the results. So we were returned 431, or a table that has 431 entries, which are these 431 solar system objects. We're then going to turn this AstroPy table into a Pandas data frame so that we can then add a column to our data frame for that orbital classification for each object. So we'll input the pericenter and the eccentricity, and it will add a new column that has the orbit class. So there's an option here to be able to print this table, which I'll just go ahead and do for fun. And you can see this column now on the right that has the orbital classification. Not surprising, most of these are main belt asteroids. Then, similar to what we did in the portal example, we can pull out all of the discoveries from this table up here by choosing the things that have a discovery submission date that's greater than 0. So we're going to extract all of those discoveries from this table, and there are 93 of them, which is consistent with what we saw in the portal. And then lastly, we're going to make a plot. We have all of our orbital classifications. We can now plot the semi-major axis eccentricities and inclinations for all of these 431 DP1 solar system objects. And then we're also going to plot separately those 93 discoveries as well. So this cell is just setting up that plot, and we're going to use specific colors and symbols between the two different plots. We're going to plot these side by side um, so that we have consistency between the markers that we're using for each of the populations. So on the left here, we've got all 431 DP1 solar system objects. And on the right, we have just the 93 discoveries that were submitted to the Minor Planet Center. So you can see we've split them up by the different orbital classes. You can see this one Trojan over here, and some of these NEOs with the Apollos and an Aten that are in all of the DP1 solar system objects. And then on the right, you can see that there's fewer objects. Most of them are main belt asteroids here in these discoveries. And the numbers in the legend here are how many objects are for each of those different classifications. So most of the discoveries were main belt asteroids. Pretty much all of them are right very close to the main belt. And then that's pretty much the end of the notebook here. We can clean up a little bit by deleting some of those of the things that we defined above. And so this is just kind of an easy example that's similar to what we did in the portal, but also now going the extra step of being able to get the different classifications for all of these objects that are in DP1, both for everything and for these discoveries separately. Okay, so we have about 10 minutes left, and that covers everything that I wanted to talk about for DP1 specifically. Uh, so I hope that all of the questions are getting answered in the chat. I am happy to pause for a second again if there's any more questions that anyone wants to ask out loud. I can't see hands raised, but you can either unmute yourself or someone who can see hands raised can call on someone. Okay, let's go ahead and move on then. So I'm going to go back into slideshow mode here. Okay, so switching gears away from DP1, I hope that all of you were able to participate in some way in the Rubin First Look media events. They were pretty spectacular. So these took place on June 23rd, and it was when the first images from LSST Cam were released to the public. And hopefully you also got to see that there were the discovery of thousands of asteroids as well that were part of the Rubin First Look event. There's a link here to the video that was part of that release of these swarm of new asteroids, which I won't take the time to play now, but I put the link in here so you can watch it again because it's a pretty fun video to watch. Okay, so I wanted to talk about some of the specifics and the differences between these Rubin First Look solar system discoveries versus Data Preview 1. So as a reminder, Data Preview 1 contains LSST ComCam data products, while the First Look has selected LSST Cam images that were selected for public viewing, but there are no data products for the First Look images or anything else. So these are two completely different things. They were two completely different cameras during two different parts of commissioning. So for solar system, DP1 has these 431 solar system objects that we've been exploring, including these 93 discoveries that are all available in the DP1 solar system data products on the Rubin Science platform. For Rubin First Look, there were 2,104 solar system objects that were submitted to the Minor Planet Center. On my last count of trying to extract things back out again, 2,098 of them are currently available, so almost all of them. However, there are no solar system data products for these roughly 2,000 Rubin First Look discoveries available on the Rubin Science platform. They're not available on the Rubin Science platform. However, all of the observations that were made by Rubin that were submitted to the Minor Planet Center and the orbits that were computed by the Minor Planet Center are available from the Minor Planet Center. So in order to give the community a way to be able to access these observations and orbits, I put together a tutorial that allows you to retrieve those orbits and observations back out from the Minor Planet Center. So let me exit out of full screen here and show you where you can access this. So going back to the Rubin Science platform, we're still in the notebook aspect here. If you go to the tutorials tab again, you'll notice that in addition to there being an option to look at the tutorials for DP1, there's also an MPC category here for the Minor Planet Center. And in it is this RFL, Rubin First Look Solar System MPC Retrieval Notebook. I've opened this before, so I'm just going to go ahead and override it again. So this notebook will allow you, as I said, to be able to retrieve all of the observations made by Rubin that were submitted to the Minor Planet Center and the orbits that were computed by the Minor Planet Center back out from the Minor Planet Center. So this uses both the GetOrb and the GetObs APIs from the Minor Planet Center to retrieve this information. So you can run this notebook and be able to pull all of these things down. You don't actually have to run this notebook within the Rubin Science platform. Since it doesn't require the Rubin Science platform at all, you can run this notebook locally as well, and it should run the same way, except for where you need to point it to an input file. So rather than running this interactively, I'm going to go back to my slides and I'm going to show you just some screenshots of this as well. So in my last few minutes, let's walk through this a little bit. So as I said, this notebook is pulling out all of the orbits and the observations back from the Minor Planet Center. So there's some initial introduction information in here about these specific discoveries and solar system objects that are specific to Rubin First Look and are not connected to DP1. So in this notebook, you do the typical import all of the packages that you need. We also need a list of all of the provisional designations for all of these discoveries from the Rubin First Look in order to use those as input in both the APIs that we're going to use for the Minor Planet Center in order to get the orbits and the observations back. So this cell points you to the place where there is a file called Rubin First Look Solar System Discovery Designations that has a list of all of those designations. So I think I have a screenshot. It's just a CSV file that has the provisional designations for these more than 2,000 objects, these discoveries from the Rubin First Look. So this just sets up that target list for all of the objects that we want to run through. We've also then got our colorblind friendly colors for any plots we're going to make. And then the first thing we want to be able to do is pull back all of the orbits so that we can do something similar to what we just did in the DP1 orbits notebook of being able to plot the orbital classifications for these more than 2,000 discoveries that were in Rubin First Look. So the query that I'm going to show on the next slide, as a warning, the reason I'm not doing this interactively is that to pull all these orbits back from the Minor Planet Center takes about 10 minutes to run this request. And so it's not something that's easy to do in real time. So this is what the request looks like. We're using the GetOrb API from the Minor Planet Center. We're turning all of the results into a pandas data frame, getting each of the different orbital parameters that we're interested in, and putting them all into a data frame, which you can see here down at the bottom. And this returns 2,098 objects in this data frame table. If you want, so that you don't have to run this multiple times, you can There's an option in here to be able to output that pandas data frame with those 2098 objects, orbits, into a CSV file. So you only have to run this once. Then there is a cell here that does something very similar to what I showed in the previous notebook that will take the orbital classifications and plot semi major axis versus eccentricity on the top here, and semi major axis versus inclination on the bottom. So these are these 2098 discoveries from Rubin first look. Here on the left, we're looking at the inner solar system, so semi major axes less than 7 AU, and on the right, we're looking at things with larger semi major axes than that. So they're all in here. You can do the same kind of thing. Next, we can also pull back the observations, and we can look at the magnitude variation as well. So this is using the GetObs API from the Minor Planet Center. And because there are something like of order 350,000 observations for these 2,100 objects, this request takes 40 minutes or more to complete. So again, a very long thing, not good for an interactive demo. This is what that query looks like. Again, you're defining all the column names using the GetObs API and setting up a pandas data frame for all of those observations that you're getting back. And here you can see we have 352,000 observations that get returned. We can make sure that we have the obs time that's returned, turn it into an actual MJD epoch as well. That's what this cell does. Then if we want to just restrict to all of the observations that were made by Rubin, you use the observatory code or station X05, and that reduces us to 343,000 observations. And again, you could write all of these Rubin discovery observations to a CSV file if you wish, so that you don't have to run these very long requests more than once. Then you can actually try to find an object that has a lot of observations. So we're just sorting the orbits table by the number of observations used in the orbit fit. If we pick the Rubin discovery that has the highest number of observations, we can then just pull that selected object out of here in particular. So in this case, we did 2025 MX21 and get 445 observations back, which we can then also we can plot. So on the left here is just the magnitude for this object over time. And on the right, we've just zoomed in on one of those particular days. And you can see that there's dense enough coverage for many of these objects that it's possible you could see some kind of variation in the magnitude as well. And maybe even do more than that with starting to look at whether there's possibilities of determining rotation periods or something like that. So I know we were at time. That is the end of what I was going to show for the Rubin first look example as well. So we do have these two separate things. We've got DP1 and we've got the Rubin first look discoveries, but we do have examples here for how you can access at least some of the information that we have for all of these objects so that hopefully you're able to go do all kinds of cool science with them. So I will stop there. And if there are any more questions, I'm happy to stick around for a little bit. But I know we have about a 10-minute break or so before the next session starts. So thank you, everybody.